This video walks through how to use the single case design hierarchical linear modeling SCDHLM web app. To demonstrate this app, I'm using data from a 2020 study by Corey Peltier and colleagues. This study used a multiple probe design across 3 small groups of 12 students struggling with mathematical word problems to examine the effect of a mathematics intervention. Once I've accessed the SCD HLM calculator, I click onto the Load section where I can upload my data. Here, you have the option of selecting an example dataset, which is helpful in practicing using the calculator. You're also able to upload data from a .csv, .txt, or an Excel file. I'm uploading an Excel file, so I will select Upload Data from a .xlsx file. Click Browse, and then locate the file with my data. The first box asks if the file includes a header. Mine does, so I keep this box checked. I'm also given the option to select the sheet of my file where the relevant dataset is located. My file has several sheets, but I know that the dataset I need is in the sheet labeled Peltier 2020, so I can select that. I then need to specify the study design. Mine is a multiple probe design, so I will select multiple baseline/multiple probe across participants. Now I need to map my variables from the file to the variables used in building the model. The app will make guesses about which columns correspond to which variables, but they're not particularly smart guesses. It helps if you can arrange your data so that the columns are in the same order as appears in the app: case, phase, session, outcome. This dataset does not have the variables in that order, so I need to modify things a bit. My case identifier is case, my phase identifier is phase, my session number is session, and my outcome variable is outcome. I also need to use the drop-down menus to specify which unique entry of the phase identifier column indicates baseline and which indicates treatment. In my case, I select A for baseline and B for treatment. If your design has other phase labels in it, like M for a maintenance phase, the observations from those phases will be excluded before fitting the model. The last optional input is to select a filtering variable. This is useful if you've got a big data set that includes some rows you don't actually want to use, such as data from cases that received a different treatment. I'll leave this blank. By the way, this data set is actually included as one of the example data sets in the app. If you would like to follow along with the remainder of this demo, you can select Use an Example and then choose the Peltier data from the drop-down menu. I can then click on Inspect to take a look at the graphs of my data. It's a good idea to compare the graph displayed here to the graph data from the original study to make sure that the data file was uploaded accurately and that you've selected the design and variable names appropriately. Here, I can take a look at the Data tab to double-check that. The graph displayed on the Inspect tab is also useful for purposes of assessing what model to use for estimating the design comparable ES. When specifying models based on visual analysis, you want to consider trends in the baseline and treatment phases. You may look at the data and recognize no trend, linear trends, or some form of nonlinear trends. You also want to consider whether the parameters defining the baseline trajectory, meaning the level and the slope, as well as the change in trajectory once treatment begins, meaning the change in level and change in slope due to treatment, differ across cases within the study, or if some of these parameters are constant across all cases. For my own data, there appears to be no evident time trend in the baseline or treatment phases, and it appears that the introduction of treatment leads to an immediate shift in the level of the dependent variable, so there's no clear reason to include slopes in the treatment phase. Next, I'll consider whether to allow the baseline level of treatment effect to be constant for all cases or to vary across cases. I can see that the average baseline level varies somewhat from case to case, so I'll want to allow the baseline level to vary by including that as a random effect. I can also see that the treatment effect varies from case to case, so I'll also want to include it as a random effect. I then move on to the Model tab to specify the model for the design comparable ES. The estimation method dropdown allows me to select between restricted maximum likelihood or moment estimation. I'll keep the default of restricted maximum likelihood, which is the recommended method. I then bring my focus to the types of time trends in the baseline phase. Again, I'm assuming that there are no time trends in the baseline phase, so I can select level. Then I opt to include level as a fixed effect and a random effect, so that the estimation of the average baseline level varies from case to case. You'll pretty much always want to include a random effect for baseline level to allow each participant in the study to have a unique initial level of performance. I now look at time trends in the intervention phase. Here I select change in level because I'm assuming that the treatment only changes the level of the outcome, not the trend. Therefore, I include change in level as a fixed effect. I'm also including change in level as a random effect to allow the treatment effect to vary from case to case. Including this random effect means that we are assuming that each of our cases might have different treatment effects as a result of the intervention. Excluding this random effect would mean that we are assuming that all cases have the same treatment effect as a result of the intervention. The last two drop-down menus under session level error structure assumptions let me select a correlation structure and variance of session level errors. These are more advanced options, so most users will probably just use the default values unless they have a good rationale for doing otherwise. The correlation structure allows me to choose which model will be used: an autoregressive model, AR1, which uses regression with previous time points to predict values at the following time point; a moving average model, MA1, which predicts each observation as the mean of past observations; or an independent model, which assumes that the deviations from the mean, in other words, the level 1 errors, are all independent. When deciding on a choice for the variance of session level errors, you can consider whether you are assuming homogeneous or heterogeneous variances for different phases. If assuming heterogeneous variances, you may choose variance differs by phase. Here, I'm keeping the defaults of AR1 and constant variance because I don't have a strong reason to use other assumptions. Now, at the bottom of my screen, I see the graph of the data with predicted trend lines based on the specified models. Inspecting the graphs lets me see if the trend lines fit the data reasonably well and gives me the chance to reconsider my model selection if necessary. Clicking on the Model Estimates tab gives me a display of the model parameter estimates based on the model specification I've selected. Now that I've settled on a model specification, I can proceed to the effect size section where I can see that the estimated design comparable ES for this study is 2.95 with a standard error of 0.28 and a 95% CI of 2.39 to 3.51. This tells me that based on this model, the intervention shifts the outcome by a little less than 3 standard deviations. The ES can also be interpreted as an estimate of the standardized mean difference that would be obtained if we could have conducted a between-group experiment involving the same set of participants, same intervention, and same dependent variable measures. The remaining numbers in this table provide auxiliary information about the model that the ES estimate is based on. The table reports the degrees of freedom reported, here 91.8, which are used in making a small sample correction to the effect size estimate. The larger the estimated degrees of freedom, the less consequential the small sample correction made, and the more precisely estimated is the scale of the effect size. Then I have the reported autocorrelation, here 0.4257, which is the estimate of the correlation between the level 1 errors of the model for the same case, different by 1 time point, based on a first-order autoregressive model. We then have the session level errors variance parameter, which we'll come back to in a moment. Lastly, I have the reported interclass correlation, here 0.0675, which describes the between-case variance of the outcome relative to the total variance in the outcome. Larger values indicate that more of the variation in the outcome is between participants. The session-level errors variance parameter becomes relevant when allowing variance to differ by phase in the development of our model. For example, if I go back to click on the Model tab and select variance differs by phase, the Estimate tab will now show the number 1.0358, which is the ratio of standard deviation during the treatment phase to standard deviation during the baseline phase. The remaining information describes the model specification and assumptions used in the ES calculations. It's included to allow for reproducibility of the calculations. Clicking on Download underneath the table downloads a .csv file onto my computer that includes all of the information in the table. Finally, clicking on the Syntax for R tab provides auto-generated R code that I can then copy and paste into R for replicating the calculations. To demonstrate, I can click Copy here and then paste this into an R script. Saving this R script can be helpful if I need to rerun the calculations. Running the code provides me with the outputs ES_RML and FIT_RML, which provide the same results as we saw in the SCD HLM app. In this video, I've demonstrated how to use the SCD HLM app to estimate a design comparable effect size for a multiple probe across participants. For this particular example, I used a pretty simple model, but of course you may need to choose a more complex model that includes time trends during the baseline or treatment phases. With these models, there are some further choices that need to be made when estimating the effect size, which I'll look at in a different demo.